Good morning, everyone. First of all, I would like to express our gratitude for this opportunity to present our research in these parallel sessions. My name is Farhana Mar'i, and I'm from Universitas Negeri Surabaya. Today, I will be sharing insights on our research, which focuses on comparing different mass learning methods, specifically for air quality predictions based on PM2.5. Let me guide you through the outline of my presentations. First, I will provide the background of this study, highlighting the motivations and significance behind this research. Next, we will explore related studies to understand the current state of knowledge in this field, and then I will explain the method used to address the research problem. And then finally, we will dive into the analysis and results, followed by the key conclusion and discussions. Let's begin with the background. Air pollution in Indonesia is increasingly alarming as evidenced by the Air Quality Index report by IQAir. AQI describes the quantitative air quality conditions determined by a region's air pollution concentrations. And Indonesia is the highest ranked country in Southeast Asia regarding to the amount of particulate matter or PM2.5 during the period 2019 until 2023. It can be seen in this picture that in 2019, Indonesia reached a level of 51.7, which is classified as a level 3 in the AQI level that is unhealthy for sensitive groups. But if we look back at the following years, 2020 until 2023, Indonesia has succeeded in lowering the IQ level, but in 2023, it increasing again. It's like 37.1. And 37.1 is also in unhealthy for sensitive groups. PM2.5 has the most significant impact on human compared to other of types pollutants. PM2.5 is the worst type of major pollutant for human health that can cause various types of serious illness and for long-term even death. So PM2.5 refers to airborne particles with a diameter of 2.5 micrometers or smaller, making them extremely small and invisible to the naked eye. To put its size into perspective, we can see in this picture, the diameter of PM2.5 is like 1 per 20 or 1 per 30 of the thickness of an average of human hair, which range between 50 until 70 micrometers. Compared to the beach sand particles, example, which average around 90 micrometers, is over 30 times smaller. Yeah. So PM2.5 is really have a tiny size and can be easily inhaled, penetrating deep into the respiratory tract, reaching the lungs, and even entering the bloodstream. So this explains their severe impact on human health. PM2.5 is mostly generated by human activities that produce air pollution, such as motor vehicle activities, power plants, industrial processes, fireworks, cigarettes, and others. So the predictions of AQI values in national cities can help the government make decisions or make policies to take preventive and mitigating measures against air pollution by looking at local air quality transfers. And then when there is a significant increase in the amount of PM2.5 pollutants. Numerous studies have explored air quality predictions by comparing various machine learning methods to identify the most effective approach. I will highlight the three case studies as example. First, Thomas M. Tilley et al. 2022 comparing random forest, gradient boosting, superfactor regression, and multiple linear regressions and proved that random forest is the best algorithms to predict air pollution, a case study in Macau. And then the next research is from Wei Fu Ding et al. 2022. He combined DTR and then feed-forward artificial neural network with backpropagations and then random forest and proved that random forest is the best notations for case study at Ningxia. And then the last is Evangelos T et al. 2022. do for LSTM and ARIMA and prove that ARIMA is the best algorithm compared with LSTM. Besides, LSTM is a deep learning, but ARIMA is the best. For a case study in the port area in a city in the Greece, that is Ikromeritsa. So, this is our contributions. Previous studies have not directly compared the three main types of methods. First is the best statistical regression algorithm, that is random forest, and then the simple statistical regression algorithm, ARIMA, and then a deep learning method, LSTM. Evangelos has compared but ARIMA with LSTM, not with RF also. So, this gap leaves an open questions about whether advanced deep learning methods like LSTM can outperform statistical regression methods such as RF and ARIMA. So, furthermore, no prior research has utilized datasets from two major cities in Indonesia that are Jakarta and Surabaya to predict air quality based on PM2.5 pollutant levels. So, this research will represent uh, predictions for the cities in Indonesia. Okay, based on the background, related studies, and the identified research gap, this study seeks to address the following key questions. First, how is the implementations of statistical regression methods that are RF and ARIMA for air quality predictions? And then how is the implementation of deep learning methods, that is LSTM? And then how are the results of comparing the performance of two machine learning approach that are statistical regression algorithms and deep learning algorithms using RMSA, MAA, and MSA. We have designed a systematic methodology that integrates data processing, model implementation, and performance evaluations. This step includes literature study, data collections, data preprocessing, design and method implementation, evaluation and method testing, and finally the result analysis. Okay. For data collections, the data collected in the amount of PM2.5 pollutants in Indonesia that are Jakarta and Surabaya obtained from the World Air Quality Report from AQAir in 2019-2023. The dataset used in study has a missing value, so we do the data preprocessing first. That in 2019, in January and April, in the city of Surabaya, and we handled the missing value with the linear regression method using existing data that are data in May till December 2019. So this is the result for our handling missing values. And then for the next data preprocessions, we do the data transformation using normalization data with min-max technique. With this formula, it is the basic normalization technique. And then after we had ready the data set, we design and we implementation the method. First, we use random forest. Random forest is an ensemble learning algorithm because it's combined two or more decision trees to improve predictions accuracy. The core idea behind this random forest is to create multiple decision trees and each train on different subsets of the data and then combine their predictions. By combining multiple decision trees, random forest achieves higher accuracy, stability, and reduce the likelihood errors that might arise from a single tree. Okay, after we do the random forest, next we do with the ARIMA. So ARIMA is the popular method that is often used to predict time series data analysis with univariate variables. This is the basic equations for the ARIMA that are the three P, Q, and D stands for autoregressive, moving average, and the number of differences necessary for stationary. So P, yeah, P is the like operator, which saves the data to previous time periods, and then P is the autoregressive coefficient for the first leg, and then theta is the moving average, Theta is the moving average coefficient for the first leg. And then mu is the constanta. Yeah. And then ET, yeah, ET is the error at time t. So the operator 1 minus b represents first differencing of the data, while 1 minus theta b represent the autoregressive and moving average parts of the model. When we multiply the equation and rearrange it, it becomes this. Okay, after we implement the ARIMA, the last we implement the LSTM. So LSTM is a recurrent neural network development method that has two mechanisms. First is short-term memory and then to long-term memory. LSTM has a more complex structure than RNN with a basic unit called a memory cell, which is designed to store information for a longer period of time. This unit is equipped with three main components, namely forget gate, yeah, input gate, and then uh, output gate. That forget gate determines what information should be forgotten or removed from the previous memory. And then the input gate sets what information will be stored in memory for the next step. And the last is output gate controls what information, yeah. So output gate is also called controls gate that controls what information will be output based on the current memory. This is the visualizations. And the input, output, and control gate are denoted sequentially as IT, T, CT, and OT is in the future. After we implement the three methods, we conclude and we analyze the result using evaluation metrics that are RMSA, MSA, and MAE with the k-fold cross validations that have 5 folds and testing data. We use 30% for the testing data and 70% for the training data. So based on the test results of the RMSA, MI, and MSA values by the RF and ARIMA, it can be seen that the smallest error values obtained by the RX random forest compared with the ARIMA. So RF is the best. Yeah, RF has RMSA 0.162 and ARIMA 0.1. It's close, but RF is the best algorithms. And when we compare with the LSTM parameters using in these experiments, the number of units of neurons is in the LSTM layer is 50, and the activation function used is ReLU. And training was conducted for a total of 50 epochs and used to a batch size of 32. So we can conclude that LSTM method are not better than random forest method, with the difference in the mean values respectively is 0.031 and 0.033 and 0.011. However, if LSTM is compared to ARIMA, it is still superior with the difference in the mean values of RMSA by an MSA, which are 0.006, 0.03, and 0.002 respectively. This is the visualizations of comparison of RM, ARIMA, and LSTM. And RF showed the best performance with small error values, and it can be concluded the RF method is superior to LSTM because the dataset used is not fully dependent on the time sequence and does not form a certain hidden pattern that causes LSTM to not work better than RF. So that's our presentation about our research. Thank you for your attention, and I'm happy to take any questions you may have.